Now let's start talking about fluids and pressure and this kind of things. You know. So a fluid. Fluids are things that flow. And to get started, I want to talk about the states of matter. Now, everybody knows common states of matter. But just to make sure we're really clear, we will start at this state here, the solid. A solid is a state of matter. Solids are typified by, and everyone knows this stuff, right? I'm not trying to insult you by saying stuff you know, but just making sure we understand distinctions for later discussion. Solids have a fixed shape and fixed volume. What that means is if I have a solid, the solid will stay in this shape no matter what I do with it within limits. Obviously, if I put enough pressure on it, I can change that. And it has a fixed volume within limits. Once again, if I press it really hard, it will compress a little bit. We say solids are incompressible, but we all know that they're compressible at some level, but not very much. What makes a solid have a fixed shape and a fixed volume? It's because of the bonds between the atoms that make up the solid. In a solid, each atom is bonded to other atoms so that they can't move. Now they can move a little bit, they vibrate. In fact, temperature is a measurement proportional to, and the proportionality actually varies by type of material, but temperature is proportional to the average kinetic energy of the molecules. So the molecules are moving. If they have a higher temperature, they're moving faster. And so the little molecules in there, see how it shows the circle with the arrows and stuff? That's to illustrate that the molecules are actually vibrating in the solid. They're not stationary. But it's like they're held, right? You have, most of you understand, we have bonds between atoms. And those bonds we treat first order kind of like they're springs. So it's like you have a Geiger counter. You guys know, what? Not a Geiger counter, a seismograph. Do you know how a seismograph works? It's really, really simple. You have a big, heavy chunk. I'll call it a chunk. And it's mounted on a system of springs. There's two more springs, one that would come forward and one that would come back. So it's just mounted on these springs. And then you have a measuring device that measures the position of that chunk. And if the earth moves, you have the inertia of the chunk that makes it resist the motion. So if the earth moves, the measurement of the chunk shows, oh, the chunk moved to the left. Well, what really happened? The earth moved to the right. And so the seismograph is measuring the displacement of that chunk. And so when the earth shakes, it sees it moving. That's how we measure the motion of the earth. Using the concept, what physics concept is that? Inertia, right. It's using the concept of inertia to measure the motion of the earth. So that's what the atoms are like in a solid. They're fixed in place by those springs. They can vibrate, but they're basically fixed. Now, if you heat them up, what did I say temperature is? Temperature is a measurement proportional to the average kinetic energy. So if I put in more kinetic or more energy, I heat it up, I put in energy, we'll learn that heat is a way of adding or removing energy. You add energy, heat flows in. You take out energy, heat flows out. Heat is actually a transfer process. You can't have a certain amount of heat. There's zero heat contained in this because heat is not something you can contain. It's only a transfer process. So you heat them up, they move faster, and eventually they're moving so fast, if those were springs, you would break a spring. So when you heat it up high enough, you break the spring and the molecules being groups of atoms, the molecules then travel alone. They're no longer fixed in place. So a liquid, so our next state here is liquid, has a fixed volume still, but a variable shape. So why a fixed volume and a variable shape? The molecules are free to move past each other, but it's still lower energy for the molecules to have other molecules from the liquid touching them. Because of that lower energy when they're touching, it requires energy to take a molecule away from the liquid. So they're flowing together, but they're not fixed in any location. So liquids will flow, they can move past each other, but they have a fixed volume, changing shape, fixed volume. And finally, our last one, the gas. And a gas has both a variable shape and a variable volume. The gas will simply fill whatever it's in. So in this classroom, we have a gas, we call it air, and that air fills the classroom. Now, if I were to get a pump and seal all the doors and start pumping air out of this classroom, it would still fill the classroom until I got the last molecules out, which of course I would never get. Even if we had only 2 molecules of air in this classroom, we would still say that the air fills the classroom because it would bounce around hitting all the walls. So in the gas, you have raised the kinetic energy enough that the molecules have enough energy to break free of the other molecules completely, and they just bounce around like they're balls in, well, you seen those little things where you get in the little chamber and they have the wind blowing, you're supposed to grab all the $1 bills? That's what a gas is like. They're like the $1 bills just flying around. That's my best example. But those aren't the only states of matter. Those are just the common ones. And some people get really bent when you skip the top one here, the plasma. A plasma is an ionized gas. Ionized means that you're not neutral charge. You have a charged gas. So you can have a bunch of electrons in a group, that's a plasma. The sun is a plasma. The temperature is so high in the sun that molecules colliding with each other cause ionization. That is, the collisions cause electrons to be torn away. So all of the atoms, except for in the outer atmosphere, have no electrons. They're all bare nuclei. And so that's definitely a plasma. And so this picture here is an example of a plasma. You've all seen stuff like that. A simple, it is mercury, what do we call them? Fluorescent light bulb. Fluorescent light bulb is a plasma. You have a gas that's basically mercury gas inside the tube, and you ionize it by sending electrons flying back and forth down that tube, and then that plasma is what is giving off the light that then the little coating on the inside of the glass absorbs the ultraviolet light created by mercury and emits visible light. And so we emit, I think there's 4 colors actually that these lights emit to give us something that looks somewhat like white. So that's a plasma. The sun's a plasma. These little things you play with a plasma. If I were to connect these to the power supply so that they were giving off light like a neon tube, that's a plasma too. Glass, we all know what glass is. We got windows. Glass is an amorphous solid. Amorphous means it's not crystalline. You don't have specific positions for the atoms. In a crystal, you have specific positions for the atoms. So something like this is a crystalline solid. Each atom has a certain position. I always want to take something like this and go to those people who believe that crystals have special magical powers and ask them, what's the magical power of this? I think it is that it will change their mind if you hit them in the head with it. But right, that's a crystal. It's not a glass because it has the specific form, the atoms all in their places. So a common type of glass here that you see in nature is obsidian. So that's the picture there. Obsidian is a glass. Obsidian can have exactly the same chemical composition as basalt and the exact same chemical composition as granite. Now, I know we're not in a geology class here, but you probably know the difference in granite and obsidian, right? Right. If you want to do something like make a tip for an arrow, which are you going to use? Obsidian or granite? Obsidian, right? When I was a kid, we'd go camping and I'd always be looking for the little Indian arrowheads because they made arrowheads out of this obsidian. Well, what's the difference in granite and obsidian if they're exactly the same chemical composition? Does anybody know? I know I'm going way too slow, but I find this stuff so interesting. Okay, a physical difference. Physical difference, you can make sharp edges much sharper with the obsidian. The reason it's like that is the rate at which it cools. When you cool slowly, you have time for crystals to form. And so granite cools very slowly over millions of years. And so it grows sizable crystals that are big enough for you can see, maybe a millimeter or so. And so in the granite, you see the different crystals. You see, oh, here's some black stuff, here's some white stuff, here's some pinkish stuff. You see the actual different crystals in there. The obsidian freezes really fast. That happens like when you have magma fall into water. Freezes really fast. There's no time for crystal growth. It just freezes and the atoms of all different types are in the random positions. And with that random position, with no long scale order, it turns out that you can break it on a very fine edge rather than on the crystal. So you get the unique glass behavior. And if you cool it a little, or if you cool it a little bit slower, you'll get basalt. Basalt is stuff that cooled fairly rapidly, but not fast enough to be a glass. It has very small crystals. So obsidian is an example of a glass. Now, our point for this chapter, the point that I've taken 20 minutes to go over, is different states of matter so that we can understand what a fluid is. A fluid is something that flows. Of the things we've talked about so far, solid, liquid, gas, the three common ones, which ones of those flow? Liquid and gas. So liquids and gases are both fluids. Now on this page we talked about a plasma. Is a plasma a fluid? It's a gas, so that means yes, it will flow. So a plasma is also a fluid. What about a glass? Okay, solid is the correct answer. But you have probably heard, most of you at least, that glass is a liquid, that it flows. How many people have heard that? Okay, a lot of us. Physicists get annoyed by this. So one physicist actually sat down and wrote a little paper about this. And of course, all materials flow at some rate. Right? If you take this iron and you let it sit here for 2 trillion years, gravity will have caused it to flow a little bit. And so the physicists calculated just how long it takes glass to have appreciable flow. And he wrote this paper about it. And one of the outcomes he said was, that thing they tell you if you go look at the windows in an old house like from the 1820s and you can see the glass has flowed, it's not smooth anymore? You guys ever heard that? Yeah, that's totally false. It's totally false. The glass flows so much more slowly than the lead that they used to hold in the window that the glass would have fallen out long before you would have noticed any flowing in the glass. That's simply the fact that they couldn't make very flat glass back then. So you're just looking at the state of glass manufacture in the early 1800s, not in the flow of glass. If you've ever seen or been on and make sure you get to one soon. A glacier. Glaciers are ice. We think of ice as a solid, but those glaciers flow. And of course, as they flow, they do some cracking, a lot of interesting stuff. But nobody considers the ice a liquid state. They consider it a solid state. Okay, the last two I have, a liquid crystal. We all have experience with liquid crystals. Your clicker, your calculator, your watch, your iPhone, they have liquid crystal displays. The liquid crystal is really unique in that it's a liquid, it flows, but it has a certain long-term order as well. And that long-term order can be modified somewhat with electric fields. And so your liquid crystal display takes advantage of that. You put a voltage across it, and it causes a rotation of the polarization of light, something we'll learn about next semester. And the final one I have here is a colloid. Colloid because, well, I am now vegan. I do love my cheese. It's just an ice cream. I know. They have butterfat globules that are suspended in a water-based solution. So a colloid is a suspension of one type of molecule within another type. And milk under a microscope slide looks like where you can see the little milk fat globules in the water-based solution. So those are states of matter. I really should have done this in 5 minutes, but I want to make sure we have an understanding. Anything that flows is a fluid, so liquid is a fluid. Gas is a fluid. Get your clickers out, by the way. Plasma is a fluid. And liquid crystals and colloids are also fluids. You understand what makes it a fluid? Because next couple chapters are on that, and so is clicker question. Whoops, didn't start it. You can't enter your answers yet. Now you can answer. Fluids are materials that flow. That is, they do not have a fixed shape. Which states of matter listed below fit the definition of a fluid? And so you're answering multiple answers and then clicking enter. Yeah, channel 33. Here you go, Trace, the man. I don't know what to say, Corso. I will read those who aren't in yet. Is it working yet, Corso? No. Channel 33. Brandon, Leslie, Corso, and it says Irving, but I think Irving's just a different.
Oh, there it is.
It has yours not entered yet, Irving? Because I think yours doesn't show up for me. It records it. Corso's finally in. Okay. It says that you've answered now. It says everyone's answered. Truly, it says you've answered. So we got 19, 21, 2, 23, 19, 21, 0. Now, I have to question if people were listening to me, because 2 people said glass. I very clearly stated glass is not a fluid. It makes me feel like I'm talking to myself. I was not ambiguous about that. It's not a fluid. Fortunately, no one said solid. At least we got that one covered. Density. Density is something we've been talking about since the very first chapter. Density has a symbol of rho, R in the Greek alphabet. Why, I don't know. And density is defined as the mass divided by the volume. And we tend to think of density as, well, it's something useful. Well, it's really useful. It helps us identify the difference in materials. When I was in graduate school, I was doing experiments with sapphire. Sapphire is a very clear material. You look at sapphire and you look at plexiglass and you look at soda lime glass, and at first glance, as long as it's not too thick, they look exactly the same. And so I have to determine, is this really sapphire? Or is it something else? Is it some other kind of crystal or even amorphous solid like glass? And so one of the first things I would do is just measure the density. If it has the right density, it's probably sapphire. If it's a different density, it's probably not. So here's a stupid question that people will be tricked with because they don't think about it. What weighs more, a ton of bricks or a ton of hay? Same, because what do they both weigh? A ton, right. But the reason people make the mistake and say, oh, a ton of bricks weighs more, is because if I had 1 cubic centimeter of brick material and 1 cubic centimeter of straw material, because the straw material is mostly air, the straw would weigh a lot less. That is, the straw is less dense. And so there's, we need to know the difference in weight and density. Pressure. Dun, 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 dun. You guys know the song, right? Yeah. So pressure is force divided by area. Now, I actually skipped a section earlier on that talked about stress. Stress is also force over area. And so people say, oh, what? How can you have stress and pressure both be force over area? And the difference is that pressure is not directional. Stress is directional. Stress, you can have compressive stress, a force that's pushing into a surface. Tensile stress, a force pulling out of the surface, tension. Shear stress, which is a force that is parallel to surface. I always illustrate, if I glued my hands to the table, I'd be genius. If I push down, that's going to make a compressive stress. If I pull up, a tensile stress. If I try to slide it sideways, that's a shear stress. Stress is actually a tensor. Who here knows what a tensor is? A tensor has more than one direction. So stress has two directions. Direction on a face that's pointing this direction with the force pointing this direction. So it's complicated. For general physics, we just talk about, stress XX on the X face pointing in the X direction, YY, and so on. Pressure has no direction to it. Pressure is always a force going into a surface. It occurs when you have fluids, stationary fluids. You'll make a force going into a surface that is the pressure. So we will talk about pressure in other situations besides the stationary fluid, like let's say Corso steps on his phone because he's texting like a... I'm not. Oh, you're not? Okay. Okay. So I just picked on Corso because he's the closest. He's not the only one who was violating the classroom rule. Okay, and he said he wasn't. I'll believe him and say he was doing something else with it. Something that has to do with class, right? Because according to syllabus, that's the only use of the cell phones. If Corso were to step on his cell phone, he would put a pressure on the cell phone, a force over the area of the cell phone. Now, which would be more likely to damage the cell phone? I won't grab your cell phone and do this. I won't.
We can try it.
No, we won't. If we were to take his cell phone, put it flat on the ground, and then put the sole of his foot on the screen, or if we were to put it on his side and put a sole of his foot on the side, which would be more likely to break it? The side. Before taking physics class, for your answer of why, what would you have said? Yeah. Because Corso already knew without taking physics class. Okay. With physics class, we can say, aha, the pressure is bigger when you step on the side because the area is smaller, and since pressure is force over area, then you're going to make a bigger pressure. And if you reach the ultimate strength, the highest stress that it can withstand, using the right term here, then it will break. And so it's going to be more damaging to put it on site, which we all know. And we can do stupid things. When I was in grade school, Sandy Pervorce, at the last day of school, she had this little needle. We were cleaning our desk, and she said, look at this. And she put the little needle here in her antecubital, and then she closed her arm over it. And it didn't puncture her at all. And I was like, whoa. And so because I had to impress Sandy, I did it too. And I was shocked. I could close my skin around it. Now with these guns right here, we'd have a problem. But back then, I had enough fat that it closed over it without puncturing the skin. And as I look back, that was really stupid, because what if it had punctured the skin? It would have been like when I tested the strength of a fingernail. You guys ever test the strength of your fingernail? No. When I was like in 3rd or 4th grade, I was standing at the teacher's desk, and I was just really bored. Because, waiting for teaching at something else. And there was a stapler, so I put it in there like, I wonder how hard I can press before the staple goes through my fingernail. And it turns out you can press hard enough to put a staple through your fingernail. Science, okay. I did a lot of science as a kid. Here's another example. We had a cat. What do they say about cats? They always fall on their feet. We had 20 steps going up to our deck, and I took our cat and I held it above the first step and let go. And it landed on its back. Second step and let go, landed on its back. Got up to about the 3rd and 4th step, and it landed on its feet from there on. It all has to do with physics. Okay, we've already actually covered this aspect. How would the cat land on its feet, and what does it have to do with physics? What was that? No, I did it as a child because I did not understand cruelty to animals. I now understand and would never do it again. What really shocks me is that the cat kept coming back to me. The cat is able to land on its feet because of angular momentum issues. It basically can straighten its body out, contort, and then bring its body back. And so it rotates without actually having any angular momentum by contorting its body, doing its rotation, and bringing it back. It's really amazing. Cats are masters of physics in one regard. They're also masters of inertia. But back to this. If you push your finger on your skin, it's never going to go through. With that little needle thing, if I did it again, I'm pretty sure it would go through. Even with a smaller force, because it has a smaller area, higher pressure punctures it. It's important. Here is a tire of our car. Well, not our car, your car, my car. And we put air in there, and you can pump up a car by hand. It'll take forever, but it has a lot less pressure than your bicycle tire. Well, if you have a chance, bicycle tire has something like 60 psi, whereas your car tire is only like 35 psi. What is PSI? What does that stand for? Pounds per square inch. PSI. The units of pressure is force over area, so pound per square inch. Now that's an obscene unit, not one we like to use in physics. What's our standard unit for force? Newton. Standard unit for distance? Meters. So we like newtons per meter squared rather than pounds per square inch. Newton per meter squared has its own name. We call it a Pascal. So we measure our pressures in pascals. So it's only 35 pounds per square inch in your tire. You put that air in, and inside the tire, that air pressure is putting a force on the surface. Now, back to what I said about the directionality. I said that pressure is always pushing in on the surface or out on the surface if you're inside. So on the tire, that air pressure is pushing out everywhere in the inside. And of course, what's important about the tire is where the rubber meets the road. So we have a certain area here, an area of contact between the rubber and the road. How is it, the more you think about this, the less sure you are of how a car stays on its tires. We have this little area. If I draw a picture of that little area, what forces are acting on that little area? Okay, there's a force normal. A force normal because that area is touching the ground. What else? Okay, there is a force of gravity. It's really small because that tire's mass is small. Okay, atmospheric pressure. On the outside, what direction is that's where the atmosphere is, right? What direction is the force of the atmospheric pressure on the outside? On the outside, the air is underneath the tire on this, because this little piece is right there. So if it's on the underside, then it has to be the force of atmospheric pressure is pushing up. And then there's one more force. The force of the air pressure inside. So I'm going to call that force, I'll put AP for air pressure. So we have those forces acting on that strip, that little piece of rubber that's hitting the road. And then I have to say, well, this piece of rubber is in equilibrium, so the sum of the forces in the vertical direction has to equal 0. Call that the y direction. So looking at my picture, I have two forces up. So when I do sum of the forces, I put the upward ones positive. And then the downward one's negative. And so now, come back to the question, why does the tire stay up? Why does the tire not collapse? I've done some physics. I haven't finished anything out. Why doesn't the tire just collapse? Okay. Pressure inside the tire is also pushing on the sidewalls and pushing up on the parts of the tire above. And so the pressure inside is keeping the tire inflated. Now, if I look at this, I can actually calculate what the relationship between air pressure and area that touches the ground will be. If assuming we have a four wheels, each, wow, my handwriting is hitting all-time greats. Four wheels each has the same force normal. If you have four wheels and each has the same force normal, then that means 1/4 of your entire car's weight is pushing down on each tire. Which of these forces relates to that? One of them exactly relates to it without any other work. Which one? Normal. The car is pressing, each tire is pressing down with 1/4 of the weight, and by Newton's third law, the force normal will be equal and opposite to the downward force of the tire on the ground. That's the force of the ground up on the tire is equal and opposite to the force down from the tire on the ground. So this force normal has a magnitude that's the force, and I'll put car for the car's weight divided by 4. What's the equation for the force of atmosphere? If pressure is force over area, what's the force equation? The force will be pressure times area. Just take this equation and solve it. So this would be atmospheric pressure times the area of the tire minus the force of the air pressure inside. That's going to be the pressure inside times the area. And minus the force gravity. I'm going to say this force gravity for the tire is approximately 0 because the rubber there that we're talking about is very negligible in weight compared to the weight of the car. And now I can determine what the pressure in the tire has to be relative to the area. So I'm going to do one step first. Factor out the area. And the force of the car divided by 4 because I have 4 tires. So the weight of the car divided by 4 tires needs to be equal to the area that's in contact from my tire multiplied by the pressure inside the tire minus the pressure outside the tire. To make our lives easy, we actually never measure the pressure inside the tire. We always measure what we call the gauge pressure. The gauge pressure for your tire is the pressure inside the tire minus the atmospheric pressure. So when you take your tire gauge has a spring and it has a piston, and you connect it to the tire, and the air inside the tire is pushing on one side of the piston, the atmospheric pressure is pushing on the other side, and then the spring is pushing with the atmosphere, and the spring will compress until the total force on that is 0. That is, to draw a picture of the pressure gauge, this is sealed. You have a spring there, and you have the pressure tire here. I changed color, sorry about that. And so looking at the forces, the force, air pressure inside, force, atmospheric pressure, and the force of the spring. That's spring written in green over the green. And you reach the compression on the spring for the net force to be 0. The amount that this had to move up to make that come to 0 is how we measure the force. So gauge pressure, important thing from this, not only working simple problems, but gauge pressure is the pressure of whatever we're measuring minus a reference, which is almost always atmospheric pressure. Buoyancy, something we'll learn about more carefully with Archimedes' principle, is the net force on an object due to fluid pressure. As I'm standing here, I have air pressure pushing what direction on the top of my head? Down, that's right, because it's going in. What direction is it pointing, is the pressure pointing for my temple? This way. On temple here, it's that way. My head's in a vise, right? The air pressure is squeezing it in. How's the force here compared to the force here? Equal, because the air pressure is the same. But the air pressure results from the weight of the air above us. So if you go up to a higher elevation, let us say you go to Pikes Peak. You go to Pikes Peak, you're what? 1.33 miles higher in altitude than you are right here. Is that right? No. What's the elevation of Pikes Peak? Like 1,400 even. So that's more like almost 3 miles, 2 and some miles. There's a lot less air between you and the top of the atmosphere there than there is here. Thus, the weight of the air above you is smaller, and thus the air pressure is smaller there. Now, as I stand here, the air pressure difference between my head and my feet is very, very small. But it is slightly higher air pressure down at my feet than it is at my head. And so there is air under my shoes. How do I know there's air under my shoes? Because I can lift my feet up off the ground with ease. If there was no air under my shoes, I'd have atmospheric pressure pushing me down, but none pushing me up, and it would be like a suction cup holding me to the ground. So I have that air pressure pushing up, but it's a little more pushing up under my feet. Now, another thing that can be confusing, you start saying, well, your body has all kinds of different curves. So that the force of air pressure here is pointing at an angle, some down, some in. Well, if you take it and add it all together, you get the exact same value. Okay, it takes a lot of hard work. But you get the exact same force as if I take what we call the cross-sectional area. That is, if you were to just take a camera and look at the outline of my body taken from above, take the area of that, we call that the cross-sectional area, and multiply it by the air pressure above, and that will tell you how much force it's pushing down. And then if you were to do the same thing from below, of course the area is exactly the same. You multiply that by the air pressure, and that gives you upward. Now we do have to admit, some parts of my body are higher and lower. My shoulders are lower than the top of my head. But if I didn't have those, that works. So you use the cross-sectional area times the air pressure, and it gives you the force in the direction normal to the cross-section. So I have slightly higher air pressure below me, hence I have a slightly bigger force pushing up than down. What does that mean? That means when I step on a scale, I actually weigh a slight amount more than the scale measures because I have a buoyant force pushing me up along with the force normal pushing me up. We didn't talk about that before we did that test on Friday because we didn't want to confuse the issue with a really minuscule force. But it's not minuscule if you'll jump in the swimming pool. If you jump in the swimming pool, the water is much more dense. What does it mean to say it's more dense? You have more mass in the same volume. I just didn't care what anyone said. So because you have more mass in the same volume, as you go down, the weight above gets much bigger. Water has a density that's about 10 to the third kilograms per meter cubed. Air has a density that's about 1.8 kilograms per meter cubed. So it's what? 800 times more dense, the water, than the air, which means the pressure difference increases 800 times faster in water than in air. So when you're in water, that upward force due to buoyancy becomes significant. And so some of us float. Back when I was your age, I sank. You know what the difference is? Density. I now have a lot more of the things we don't like in our body that have low density. Back then, I had a whole lot more of, the fibers and the muscles that are more dense. And so I sunk. It's sad, but true. Your density is made up of materials you're made up, and I am now less dense. Okay, we're out of time, so we will pick up with this next class period.